I'm sitting here in front of the UK's first quantum networking experiment. What this experiment does is generate entanglement between trapped ion qubits, which are separated by a macroscopic distance of about 2 meters in the lab. One is trapped in the vacuum system over there behind me, one in this vacuum system next to me. And those single atoms are linked by single photons of light, which are captured by a high numeric aperture lens here into optical fibers and made to interfere. And with this process we can generate entanglement between these two remote qubits with a speed and precision which is unmatched by any other experiment in the world.
For building a quantum computer, there are these 5 DiVincenzo criteria. So we need qubits, so a bit that follows the quantum rules, so we can put it into a superposition or we can get entanglement. We have to be able to read it out and prepare its state. We have to be able to do operations with a high fidelity on it. And we have to be able to scale it up to very large system sizes. Trapped ions are something really exciting in that we can trap single atoms in an electric field, which is something that 100 years ago some of the most famous physicists thought would never be possible. When we trap them, we can excite them with lasers and they shine light like a little star. We can see them and therefore read them out, which is a very important property that we need for a quantum computer.
What you're seeing on screen now is 2 ions. They are trapped inside an electromagnetic field that is inside a vacuum system. And the reason you can see these ions on camera is because we're shining laser beams at them. The ions will absorb photons from the laser beams we shine at them and then re-emit them in all directions. Now the cool thing is I can change the behavior that you're going to see on screen now by changing the wavelengths of the light that I'm shining on these ions. So now what you can see is the ions flashing between bright and dark. What's happening here is you're seeing quantum jumps. The ions, when they're dark, what's important is that they're still there, they're just in a different internal state. These different states that the ion can jump in between, we can call these states 0 and 1, and this is the foundation of performing quantum logic with these ions.
Right now we are trying to improve the quality of the entanglement that we have. So right now we can generate raw pairs of entanglement with reasonably high fidelity, but we are aiming to perform a protocol that is called quantum distillation, entanglement distillation. And the idea there is that you generate several pairs of entangled ions and then do some operations on them and you create a very good single pair of entangled atoms.
This networking experiment is part of a longer-term vision of scaling up the most precise qubits we have, those based on trapped ions, into a practical quantum computer via a networked or modular approach. So the idea here is that by building multiple modules with a relatively small number of qubits and then linking them together optically via a network of optical fibers, that is one route towards building a large quantum computer which can solve all kinds of problems which our conventional computers find intractable or impossible to solve.